will trickle in. That's okay.
Sure. Should I give it one more go on my end? Ashley and Matthew both sent me links. So if I can't share from my laptop for some reason, I can send those links on to Nick. Nick, if you could share them at your end.
Sure. Yeah, we can give that a shot.
All right. Well, let me have another try. I'll see if I can get this to work.
So for people who are joining, you're in the right place. We are doing some testing and checking, and we will start in a few minutes.
Okay. What do people see? Do they see Matthew's?
We are sharing, but we once again have the grayed out regions.
Yeah, that's because I came back into Zoom. I need to make all the Zooms
out. We should be okay.
Zoom bits and pieces.
This is much better. It might be acceptable. There is only some little thing at the very bottom.
Yeah, that again is the Zoom bar.
Looks like that.
If I actually make my QuickTime window smaller, it won't. The Zoom bar shouldn't encroach on it. Now it's within the Zoom.
Yes, now it looks okay. I mean, right?
Okay.
Yeah, that looks good.
Yep.
That looks as it's supposed to be.
Great. Okay. Then I will stop sharing and I won't touch anything. And it'll all stay exactly where it is.
Anne-Marie, do you want to quickly check your test your connection before we start?
And Ben, you're just going to take it away, okay?
Yes.
At the start of the session.
Sounds great.
Sorry, what did you say, Avi?
Do you want to test your connection before we start?
I think I'm good.
Okay. So Ben, the floor is yours.
All right, great. Should we just start right up, or should we give people a minute? Let's start. Let's start.
Yeah.
It's 5:30. All right. Good morning, everyone. Welcome to session 6. We're excited to start off with a panel today. My name is Ben Monte. I'm a lecturer at the University of New South Wales in Sydney, and I'll be the moderator for the panel. I feel very lucky for this panel. It's a great group of people. We're privileged here that yesterday, the exoplanets panel, good panel, but there were no exoplanets themselves on the panel. Today's the Young Stars panel, and we have 4 young stars to speak to us. So can't do better than that. We have Jason Curtis from Columbia University, Anne-Marie Cody from the SETI Institute, Ruth Angus from the American Museum of Natural History, and George Zhou from University of Southern Queensland, just up the road a piece from me. So we'll begin with each panelist spending just a couple minutes telling us an overview of their talk, which I know you've all diligently watched before this. And then we'll jump into the discussion. So if you have any questions for the panelists, we will be using the Young Stars channel, which is I will have open and be paying attention to. And so please ask your questions and we'll hopefully have a very good discussion over the next 50 minutes. So Jason, why don't you go first?
Hello. Gaia and TESS unveil a remarkable diversity of young clusters in the solar neighborhood. Gaia data, parallaxes, proper motions, coordinates, etc., have been used to find all manner of stellar structures within a kiloparsec of the sun, even beyond. Known clusters now have much richer membership lists, but when we relax the constraint of focusing in on kind of the core region and look for co-moving stars, they're actually found at quite large distances. Halos and tails stretching hundreds of parsecs in space. New kinds of structures are found, amorphous blobs of stars, elongated streams or strings of stars. And what TESS provides is a means for demonstrating that these structures are actually composed of stars that share a common age. I'll give one example here. So Marina Kunkel and Kevin Covey found 1,640 structures within a kiloparsec of the sun, including Gaia 520, you can see here in blue. What's special about this cluster, or this grouping of stars, is that it's actually home to Kepler 52 and Kepler 968. So what that means is that this is in the Kepler field, and we didn't know about it at the time. It's actually just at the edge of the Kepler field, so even if we knew about it, we probably would have gotten more stars. But this actually sits above the, slightly above the Kepler field, and reaches up into the TESS northern continuous viewing zone. So the question is, are these multi-planet hosts that have 3 confirmed planets each from transit timing variations, are they actually siblings? Are they part of a larger structure? And if so, what's its age? And oops. So for this, we appeal to gyrochronology, the process of telling time with spinning stars. And we'll hear about the gyrochronology models and our attempts and failures to build an accurate model. But what's important is that when you take a group of stars that were born together and you plot their masses versus how fast they spin, the stars organize themselves into discrete structures or sequences that are unique. And so whether or not we can accurately model it, we can tell if a group of stars share a common age based on their rotation period distributions. This is where TESS is critical. So for this particular grouping, say at 520, we measure rotation periods largely from TESS, but also from Kepler, and also importantly from this Zwicky transient facility, which is an important complement to TESS. And what we find is a tight sequence of stars, which shows they share a common age overwhelmingly. And while the color magnitude diagram for the cluster is shown on the bottom right, it looks convincing enough, looks like a cluster. The problem is that the upper main sequence in the upper left, where all the age information is encoded in this diagram, is too sparse for us to confidently age date this group. So gyrochronology, the rotation period distribution from TESS, provides us the means to prove that these structures are real, what their true extent is in space, and constrain their ages. And so I'll just close by showing some top-down and side view of some local young clusters, kind of based on Gaia data, traditional view, compact cores, and the expanded view, from one approach and an alternative approach. And so we get very different results based on how the Gaia data are searched. And so, and I'll also remind you of what star clusters look like when they're born and what groups of stars look like when they're born. These are ongoing and recent sites of star formation, lots of substructure, age gradients, diffuse populations, dense populations. And one thing that's helping make progress here is the large amount of data that lives on the internet for free. Gaia astrometry and photometry, time series imaging, spectroscopies, starting to amass large data sets online. This is very useful for us, but it also removes barriers to entering research for other people. So I think that's great. So that's it.
Awesome. Thanks, Jason. Anne-Marie, how about you? You want to go next?
Okay, thank you. I will show a few highlights from the talk that is shared online. A moment here. Okay, can you all see that okay? So I am mainly interested in young stars, and young for me, I always like to point out means about 1 to 10 million years old. Who you ask, you might get a different answer. And I'm particularly interested in the young stars that have circumstellar or protoplanetary disks left over from their formation. So this is a schematic of what's going on around these young stars. So you have this, the star in the center, you've got magnetic field lines, which are probably more crazy than this, gas falling onto the star, dust swirling around. Basically, it's a pretty crazy environment, and planets are forming somewhere in this disk. And that environment translates to a whole lot of variability that we can see with TESS, and we have seen previously with other space telescopes like Corot and Kepler. So in my video, I give a summary of what we have seen with those previous telescopes. And then what I want to highlight here with TESS is that we're moving to higher mass because the stars with masses greater than that of the sun are brighter, and they're really the best targets for TESS. Not that I want to leave the low mass stars behind, but we're really starting to explore the differences in environments between the low mass and the higher mass stars, and we're starting to find some very interesting things. It's thought that the magnetic fields and the location of the inner dust rim is different as you go out from, say, KM stars to now A and B stars. So I don't really have the time to explain all of these areas, but these are just some of the things that we can touch on by studying the light curves of young stars. In particular, we can look at the structure and dynamics of dust in the inner AU surrounding them. We can get clues as to magnetic field geometry and generation from accretion and study of star spots. Eclipsing binaries. There are potentially some substellar companions, but they're hard to find among all the variability. And then thanks to TESS revisiting things in many different sectors, we get to study also the stability of all these processes that are going on and at time scales anywhere from minutes to years, as far as we can tell, with in some cases fairly substantial amplitudes. So where TESS comes in for us is not necessarily the high precision that helps, but the continuous monitoring every at FFI cadence, essentially. So I'll just whet your appetite with a couple light curves, but there are many more in my talks. Some of the light curves, some of the objects display fading events. We've come to call those dippers. These are usually signs of dust occultation, where you see the light curve go down by about 20%. This is a Herbig star, so it allows us to assess what's going on in the inner AU or even sometimes further out in terms of the dust structure. And then the interesting things that I highlighted in the talk is that at low mass, we have a lot of quasi-periodic behavior where there are structures in the disk that are in orbit and repeatedly occulting the central star. They seem to disappear at higher mass. This is one of the few objects where we see it, and that's telling us something about the inner dust rim of the disk. And then finally, there's a lot of speculation about, are there magnetic fields at higher mass? Are there star spots? It was a long time ago proposed that there weren't, and we're disproving that. We see periodic behavior in the light curves, and that indicates star spots on the surfaces of these objects, even at masses higher than the sun. So these are just some of the takeaway points that you can get if you haven't watched the video yet, and I'll leave those up there.
Great, thanks, Anne-Marie. I love that schematic on your first slide. Probably give a 3-hour lecture just explaining the detail in that. So rich. Yeah. Wonderful, thank you. Ruth, can you go next, please?
Hello, yes. Okay, so my talk is on stellar age determination, and I really, in the long version, I just mostly talk about gyrochronology, so rotation dating. So gyrochronology is the method of inferring a star's age from its rotation period and either its temperature, color, or mass. And we know in general that stars lose angular momentum over time, and so they move upwards in a diagram of rotation period versus temperature. And we can use empirical or semi-empirical models to relate the three things together. So if you have a rotation period for a star and you know its temperature or its color, you can infer its age using a model like this one, which is one of Jem Van Seder's gyrochronology models. So we know in bulk that this works. We know that in general, the rotation periods of stars lengthen over time. We see that pretty clearly in the data where we have ages of stars and measured rotation periods. But in detail, we don't have very fully calibrated gyrochronology models across the board. And so in my long talk, I describe all the ways in which the gyrochronology models still need some refining. And I use the Kepler rotation period sample from Chontos et al. 2021 to describe all of these areas. So again, this is rotation period versus effective temperature for stars observed by Kepler. And these are the areas where the gyrochronology models are still being refined. There do exist some gyrochronology models that work well in some of these regions, but in others, we really need more data to calibrate them in more detail. And that's where TESS can come in. TESS can provide rotation periods and ages for stars in new moving groups, open clusters, stars with astroseismic pulsations, stars with co-moving white dwarfs, and there are many ways in which TESS can help with this problem. Given that this is the young star panel, let me just say a little bit more about young stars. So this is a figure from one of Louisa Rebel's papers, which shows different open clusters of different ages, increasing left to right and top to bottom. Again, rotation period versus now color. And this shows that the rotation period distributions of stars quite clearly evolve over time, and they become more and more easily determined by a single sequence that relates period and color. But when they're quite young, the distribution of rotation periods is much more stochastic. So if you have a rotation period for a young star, it can be quite difficult to precisely determine its age. If it's between 0.1 and 10 days, it could be consistent with any one of these ages. So some care is needed when trying to apply gyrochronology to young stars. The conclusions of my talk are that gyrochronology is very promising. It's a really promising method. It could be the only way that we could measure precise ages for K&M dwarfs on a large scale. And TESS will help us refine the gyrochronology models. One other thing I talk about in my long talk is that we need to use care and specialized methods to measure long rotation periods with TESS. I'll leave it there. Thanks.
Thank you, Ruth. And George, will you bring us home?
Yeah, thanks very much. So I'm just going to start with this toy model of how planets form that you've seen before. You start off with gas and dust, and as the gas and dust coagulates and the dust moves inward, they form protoplanet cores. The cores attract the gas around it, and that gas and the core makes the protoplanets that we see. Over time, that gas and dust disk dissipates, and you're left with these young protoplanets. And they get subjected to the intense X-ray and UV radiation in the young star, from the young star that is harboring them. Eventually, you're left with these star planets of various densities. Some have been formed and shaped by evaporation processes, some by dynamics. And so what are the outcomes of this toy model that we have? The most simple and testable of which is that these planets, especially the young ones, should exist in orbital planes that are well aligned with the plane of the protoplanet disk from which they were formed. Is that what we see for planets around older stars? No. Planets from older stars, I'm plotting especially here small planets that we've characterized around mature age stars, can be found in all sorts of obliquities. Sure, there are the planet systems that are found in well-aligned obliquities, but there are also those, both short period and longer period, for small planets around mature age stars that are found in various sorts of polar retrograde orbits. Now take a look at the obliquities of the planets that we've measured around young stars to date. Because of the observations from K2 and TESS, we now have half a dozen planets for which we've measured the obliquities for with spectroscopic transit observations. And we found that they are all very much well aligned with the protoplanet disk. So when does that pumping of inclination happen? That's something that we can investigate by observing more of these systems as a function of age to observe how the obliquity gets changed over time. The other outcome is that the densities of these planets should be a function of age as well. It's an extra dimension to the well-known period, mass, radius distribution. And so if we let our planet systems evolve, they get shaped by evaporation processes and by mass loss processes. And that's how we come to see the mass radius diagram, the period radius diagram that we know so well from Kepler. In the closing end, we have X-ray radiation shaping the sizes of these planets by photoevaporation, core heating for planets of longer periods. We can see this happen with young planets. We can measure the masses of some of these young planets. Case in point, the Harps North measurement for K2-100b. We can also see mass loss as it is happening. A great example is the recent observation by Zhang et al. For HD 63433 in Ursa Major. where they see the Lyman alpha escaping atmosphere. These are the observations that we hope to make in the near future for these young planets. And these are all enabled by the great discoveries that we have. This is age versus magnitude for the young planets that we have so far, and these are the planets that have been discovered by TESS. TESS is making all these great discoveries for planets around young stars that are bright, that are enabling these characterization observations, and we hope to see many more of these in the near future.
Wonderful, thank you. You also have, those are some very nice slides there. I really like that last one, the drawings about the planets. Cool. Okay, so thank you all for your short presentations. And we had a just question on the Slack here of where can I see the longer presentations. They're all on YouTube. I've dropped the link into the Slack, so feel free to watch those or rewatch those at your leisure. And they'll remain far after the conference, and so they can be a repository, hopefully for pedagogical purposes in the future. So if you have any questions, drop them in the Slack and we'll use them as the basis for a discussion. I'll use moderator privilege to ask the first question. And I think I'll ask Ruth to speak first, although everyone else can jump in afterwards. We know that one of the challenges from TESS is long-term systematics. There's the Earth shine is very dramatic, and every month we step to a different sector, and so stars land on a different pixel with its own sensitivity. And so one of the challenges can be looking at long-term signals, slow rotation periods, some of the smaller scale variations in Dipper stars. So how do you get around that? How slow do you think you can go for TESS rotation periods? And do you have any advice on how to best recover slow variability, not sharp transits, but slower variability like rotation periods?
Yeah, thanks, Ben. So from the work that I've seen, it can be really difficult to measure rotation periods longer than about 13 or 14 days with TESS. That's both from single sectors and from stars with multiple sectors that are stitched together. It's really difficult to measure periods longer than that, regardless of how many sectors of data that you have. The sort of methods that I've seen that have worked really well for recovering long-term variability involve detrending the light curve and fitting a model for the astrophysical variability at the same time. So as you detrend, you fit something like a polynomial or a sinusoid at the same time as the co-trending basis vectors or whatever you're regressing against. And that can preserve that long-term variability. So Soichiro Hattori has a paper on the archive. There's a code that he developed called Unpopular, which uses causal pixel modeling, which does this really effectively. And Christina Hedges also has a tool called the TESS SIP, which she published as part of an RNAS last year. Those are two methods that are promising for preserving long-term variability.
Great.
Oh, and let me just say one more thing, Ben, sorry. This is a problem that's relevant to young stars because young, and again, it depends on how you define young, but at Persepi's age, so 500 million years or so, M dwarfs are rotating more slowly than 13 or 14 days. So it affects young stars too.
Yeah, absolutely. Thanks. Any other panelists want to add anything to that? Okay, all right. You don't have to. We have a lot of other questions coming in here. And so I'm going to try to get through as many as we can. We'll see if we do, we'll start with a question from Luke for Anne-Marie, Luke Bauma. Are the rotation signals for high mass stars consistent with their equatorial velocities, or could they come from unresolved binary companions?
Yes, that's something I'm starting to look into. We also, I should have added, have an issue with a little bit of sample contamination. There are lists of young high mass stars in the literature, and high mass stars evolve quickly. So sometimes you get things that are not on the pre-main sequence that have evolved beyond that and are actually pulsating. So for the most part, I'm trying to remember what the general periods would be, but they're pretty fast. And so some of these may be spurious for sure. We're talking about like days or a day or so. But there are cases where we're seeing like one of the examples I showed was, I think, about 2-day period where it is consistent with the star's rotation period, but there are other things going on. And yes, we can have lower mass companions, but typically the brightness of the higher mass stars is dominant enough that you would only be suspicious if you have a very low amplitude periodic variability that suggests a blend. So I think we are seeing multiple different things going on, but some of it is star spots on the surface, some of it is not. Maybe not a very satisfying answer, but in the process of sorting through it.
It's amazing how many answers are it depends when it comes to young stars. Binaries can be in effect for all 4 of our panelists. Do any of you want to comment on how binaries are or are not a problem for some of the work you talked about? And by problem, I mean opportunity. Of course, binaries are great.
Is that for me to start or everyone?
No, I think you gave a great answer. If you wanted to add anything about binaries, go right ahead. And otherwise, any other panelists could jump in.
Yeah, I will admit, I mean, I dealt with it already with earlier samples from K2. And my idea of going to the high mass brighter stars was an acknowledgement that I'm attempting to avoid that problem right now. But it will be good to move toward lower mass stars also with TESS, because we are revisiting some of the K2 fields very soon. And we're going to have to figure out how to deal with that a bit better. And it's more difficult with the crazy kind of variability that I deal with to sort out multiple signals from each other. But there are ways to do it in terms of changing your photometric aperture to be very small and moving it around and seeing where it actually comes from.
There's something to be said for just avoiding or finding the low-hanging fruit. Just if you can avoid a problem and deal with it later, let future Anne-Marie deal with it. Cool. Any panelists have anything they want to add? Go ahead. I think Ruth and Jason, you've unmuted yourself. You're all very polite people. Just go ahead and jump in. There's only 4 of you, so we'll just jump in. We'll figure it out.
Jason, you go ahead.
Okay. For like rotation, there are some issues with binaries because short period binaries can tidally interact with each other, change how fast the stars are spinning, prevent them from spinning down, spin them up. Wider binaries can affect things like the lifetime of circumstellar disks, which can affect the initial angular momentum. One interesting thing that came out of some of the older clusters observed by K2 are the presence of rapid old stars that don't appear to be binaries. So Emily Leiner termed these blue lurkers because she thinks they're blue stragglers, so stars that transferred mass or merged together and so spun the star up, but didn't receive enough mass to push them beyond the main sequence turnoff. And so in Ruprecht 147 and also in M67, we're seeing these rapid stars that appear single in every kind of way, with adaptive optics, with the Gaia Rui, with long-term RV monitoring, photometry, so like, but they're spinning rapidly. Now, it's possible that these used to be binaries and are not any longer because they merged together. And there's a lot of them too. It's a large, so are there a lot because it's a dense cluster where these dynamical interactions is probably greater than in the field? It's hard to say. So that's one thing I'm concerned of is rapid stars that used to be binaries, and it's hard, or it's hard to tell that they're binary. So I don't know. Reina Rampali also has a paper now on Praesepe, which is like the most complete view of rotation in Praesepe, and shows the impact of or just the binaries largely follow the single stars through the color period diagram. but also a lot of the outliers from that slowly rotating sequence happen to be the binaries. So we're still trying to understand like why they agree sometimes and why they disagree.
Yeah, I think that's a great question. And I think, of course, binaries present a huge opportunity for planetary and young stars. I want to use that opportunity to address Brett Skinner's question on Slack, which is how might orbital inclinations of older planets be explained besides interactions with other planets? Well, stars could be one such interaction. I think DS-TUC, the very first young planet discovered by TESS, is one of the great examples. It's a binary system, DS-TUC A and B, that are visually separated. And by looking at the obliquities of that planet system, we were able to understand whether DS-TUC B was dynamically migrated to where it is right now, or whether, for example, it might have formed there. And in this case, we found that it was well aligned, whereas dynamically it would have been inclined. And so I think by making these observations for a larger number of planet systems at a variety of ages, you can then be able to start telling us when these inclinations get pumped up and when do these dynamically migrated planets actually come in, because the actual pathways of dynamical migration have very different timescales.
And can you give us a ballpark of what those timescales are for people that might be unfamiliar?
Yeah, so, if you have very simple quasar scattering, it can be very, very quick. And if that was the case, and if we are starting to find hot Jupiters at 10 mega years that are inclined, then that could be a great example, or 10 to 50 mega years, that could be a great example that might be happening. What if we start seeing only hot Jupiters at 200 mega years that are misaligned? That will tell you something different.
Great, and we have clusters that go out, as I forget who showed it, but we have things in TESS as young as a few million years up to clusters out at 700, 800 million years. So there really is a broad sample here. While we're on that topic, Jim Davenport had a question for Jason and Anne-Marie. Are there more young clusters that we can use to build out samples of young stars at critical ages? Where have we not looked yet that we can be looking?
Well, I think there are areas on the sky that TESS has looked at, but are not very well appreciated young clusters. One thing that I'm starting to do is do a bit of a blind search for young stars based on their variability. Haven't gotten too far yet, but we have found some interesting things that are trying to remember. There was a cluster in I get the two constellations mixed up, but it was either Camelopardalis or Cepheus. Anyway, it was a cluster that I wasn't very familiar with, and there was only like one paper published on the membership. And we found a Dipper star in there. So there's surely a bunch more, but for various reasons, people have not really assembled the cluster membership from ground-based telescopes very thoroughly. So there are at least some, in addition to sort of the classic young clusters and associations that were looked at by K2 because they're a bit farther out of the ecliptic. So we could certainly take a look at those.
There are tons of clusters at lots of ages, and it's hard to know where to start. There are just so many interesting things out there, new things being discovered. So this is how actually I stumbled across the F520. So critical ages, what are those critical ages? Depends on what you care about. If you want to find dippers, you have to go like to the very young route, right? Like less than 50 million years. But from a gyrochronology perspective, what I've been interested in, I've been actually focused on, I don't even know what I'm doing here, talking about young stars. I've been working on very old clusters, old being like 3 billion, 4 billion year old clusters. And one of the things we're finding is that these star clusters around the K dwarfs are having rotation period sequences that are overlapping or too close to each other based on our incorrect understanding of how stars should spin down, despite them being like twice their age and stuff. So what I realized would be a good avenue to do is to figure out when do these slowly rotating sequences form. And so to do that, we have to go younger than Praesepe. And so what I'm trying to do is fill in the gaps between the Pleiades at around 100 million years, Praesepe Hyades at 700 million years, both done very amazingly by K2. But the intervening years where these sequences are finally converging and starting to evolve, and possibly also starting to stall at higher masses or pause, it's a bit more uncertain. There's less data available. And so there are like hundreds of these things. And so we have to sift through them carefully to find the ones that are most promising. But once we find one that looks like it has a good membership list, maybe, that has rotation periods that are measurable with TESS, well, it doesn't stop there. We have to actually characterize it. And so we need follow-up spectroscopy. Some of that's already living on the internet, but some of it we have to actually propose. We have to go out and actually collect these spectra and analyze them to get things like the metallicity, to get the interstellar reddening, so we can actually make sense of what's going on. At the younger ages, even younger ages, Louisa Riebel and Stephanie Douglas have posters on the very younger ages that have not really been explored that well. And so I'm hoping, like Stephanie is focusing on these like 40 or 50 million year old clusters that are really proper benchmarks. They have ages from like lithium depletion boundary, which are like very trusted. And so once I think we have a sense of what's going on there, I think we can really broaden our perspective and really find these new things so we can compare them to the benchmarks.
Cool. You mentioned in your talk age dating a new cluster just in and off of the Kepler field, and Pisces Eridani is well known as a cluster that was discovered fairly recently with Gaia and identified as being young by work by you and others. Do you think we found them all now? Are there some young clusters nearby that are still to be found, or do we have the full set?
I think there are going to be more found, and some that are found will turn out to not be real clusters. That happens. But the Thea catalog, led by Marina Kunkel, and other attempts to find these things are clustering on astrometry, which depends on like where in the sky the thing is. And if it's too close, it's all around us. In some cases, like the AB Doradus moving group, it's hard to use proper motions and stuff alone to find these things. And so radial velocities would sure help define these. And I think over the coming years, we'll find more structures that are like very close by all around us. Also things that are a little smaller, cluster remnants or more diffuse groupings.
Great. And so we know there's a big diversity of stars that are formed in clusters. Different clusters can look very different. There's also diversity of the planets. This is a cheesy segue to get to a question from Heis Mulders for George. In your planet formation toy model, you have your planets starting volatile rich and then losing their volatiles over time. But planets form in a diversity of ways. So what about planets if they're born volatile poor and then gain an atmosphere through outgassing over time? Would you see something, could you determine that? Could you understand that? Tell us about, the primordial atmospheres.
Yeah, I think that's a great question. I think it goes back to the sample that we have. So going back to Jason's point, and I think that was a great point, if we rely on the classical clusters, you have, let's say, 1,000 members in Hyades, 1,000 members in Pleiades that are characterizable and that were surveyed by K2, for example. You're only expecting to find 1 or 2 planets. And you need 10,000 planets, for example, to find 1 hot Jupiter, even if the occurrence rate was there. So the point is that if you only have the single-digit number of planets as a function of various ages, you're not going to find the distribution. And to be able to find the distribution, we need more of these young stars. To go back to that particular question, we should be able to see the difference in period in radius distribution as a function of age for these types of planets. And right now, the smallest planets that we can find around Hyades age stars is about 1 to 2 Earth radius. This is, for example, from Aaron Rizzuto's great work for K2. And so if we were to only find 1 to 2 Earth radius objects, and the number density of these planets were not to increase as a function of age, maybe they gain their atmospheres that way. But if we were to find a paucity of 1 to 2 Earth radius planets at a very young age, but then they start forming at 800 million years, for example, then perhaps that's a great example of when the planets lose their atmospheres and expose their cores.
Great. There's a question for Ruth in here that I'm also going to ask Anne-Marie to comment on from Thomas Steindl. You mentioned the problems of gyrochronology for very young stars, Ruth. What do you think is the influence of early accretion onto the rotation period of these young stars?
Yeah, so I'm sure that will have an effect at the very young stage. It will change the rotation period of the star. But for gyrochronology purposes, I would say that's when that's happening, stars are probably so young that gyrochronology isn't yet applicable. So it takes them a while to contract onto the main sequence and then launch their winds and begin magnetically braking. And the time at which that happens is different for stars of different masses. So in Persepi, for example, the M dwarfs haven't even started that, or some of them have, but a lot of them haven't, at about 700 million years. But in some young clusters, 10 million years, 100 million years, we see the higher mass stars have already started this magnetic braking. Disk locking can be an effect too that really influences a star's early rotation period. So magnetic interactions between the disk and the star prevents the star from spinning up as rapidly as it might do if it didn't have a disk. So that's one of the reasons why binaries can influence the rotation periods of stars. They can truncate the disk and prevent that disk locking from happening. Anne-Marie, did you want to add?
Yeah, I was certainly going to mention the disk locking. I mean, and I would refer you to the work of Louisa Rabal, who has a poster here. She's spent a lot of time measuring rotation rates for the youngest stars and also looking at not only how that depends on their mass, but the presence of disks. And the disks tend to disappear somewhere around 5 million years or so, and you can definitely see a difference in the rotation rates for the disk-bearing stars and the disk-free stars, depending on what's happened. So the stars tend to be born with a whole range of rotation rates, and as Ruth mentioned, it's not until much later that these clear sequences start to appear. So we have other methods of age dating the youngest stars, looking at not only the HR diagrams, but things like lithium. The rotation rates are still kind of messy enough at that age that they're not that useful for telling how old a star is. But yeah, definitely go chat with Louisa Rabal. She's the expert on that.
Ruth showed some beautiful GIFs at the start of everything kind of coming together and then starting to move upwards again. There's an implicit assumption when we use that for gyrochronology that they all converge to the same point, like you just converge to a point at a certain age. Is it necessarily true? Things like metallicity matter. What if they all converge to slightly different points? How worried should I be? I suppose that's for anyone who wants to answer.
I like this is a question for Jason.
Yeah, metallicity is a tough one. There's two ways to approach it: with data and with theory. So me, being someone who studies clusters and measures things, I'll talk about the data. So, we have star clusters. We have star clusters that have same age and different metallicities. Now, these aren't wildly different metallicities, but they're different by like 0.2 dex. So it's a start. And, so what we've done is we used TESS and ZTF, but mostly TESS, to measure rotation periods in the Coma-Berenices cluster, which shares an age in common with the Hyades and Praesepe, but which has a metallicity that is significantly lower, 0.2 dex lower. When you plot rotation versus photometric color, or converting it to whatever you want, they overlap basically identically. And so my hope, this has been the hope all along, is why all these models are tabulated in terms of photometric color, not just because it's the most abundant measurement of something's mass proxy, but it also helps mitigate some of the metallicity of impact that you'd have if we can magically have absolute masses for everything, which we can't. From the theory perspective, you can model like, stellar isochrones, like how does metallicity affect like the stellar structure, the depth of the convection zone, and all these kinds of things. And you could do that, and you can have metallicity. You can show that there's a metallicity dependence for rotational spin down as a function of mass. But again, I think in those theoretical models, when you instead analyze things in terms of temperatures, it's largely mitigated, which is nice. But I think it's still an open question.
Great, something to look forward to. All right, we have a little less than 10 minutes left. So I have a few questions for all of you that I would like to hear your answers on. So we're going to move to a lightning round. I'll ask some questions, then we'll just quickly step through what are your answers from each of you. First is a question from Nicole. What are you looking forward to from TESS looking in the ecliptic, revisiting K2 fields? What can we learn from there? Let's go in, we'll go in the original order from your presentation. So start with Jason.
Well, in my extended talk, I talked about what makes TESS so special compared to K2 and Kepler. I mean, hard to compare the data quality, but it's not having to know what targets are special ahead of time. TESS observes the entire sky, or large portions of it at least. And we'll soon have the ecliptic in whatever cycle that is coming up. So what we're going to have is the ability to measure rotation periods for stars we didn't know were special beforehand and didn't get apertures assigned to them. And so there's one special cluster. It's another Theia group, Theia 303. My team of high school students at the American Museum of Natural History was studying it because it has a K2 exoplanet candidate. Only 4 of its stars out of hundreds of stars were randomly observed by K2, 4 of it, and one of them has a planet. And there's hundreds of stars sitting on the Campaign 7 all across the field of view and even beyond it. And we could have measured those rotation periods if we knew they were special stars. We didn't plan for that. But now if we get TESS to look there, eventually we can do that. And that's important for showing that it actually is a real cluster and for validating its age.
Great. Anne-Marie, what are you excited about in year 4?
So it's hard to beat K2 mission, but one thing that TESS has that was not common for K2 is pointing at targets that are visible from the ground. So we're going to be doing that, for example, in the fall with the Young Taurus Association, which is a few million years old. And one thing that's been missing for a while is multi-band photometry to actually assess what's going on with the variability or certain color trends you'd expect from dust versus star spots versus something else. So I have acquired a little bit of ground-based time where I could simultaneously monitor a relatively small number of targets, but a number of young stars that will be getting TESS data and have previous K2 data. So like Jason alluded to, we have prior knowledge of at least what the stars were doing couple of years ago. That may change, but I'm excited getting this complementary data that is taken at the same time as we see it with TESS, which is not something we've done much of before.
Cool. Ruth, how about you?
It's going to be so incredible to have more targets with known rotation periods overlapping with TESS. That's going to be so important for rotation studies with TESS. A lot of sophisticated machine learning based methods for vetting have been developed. So for example, the Breton 2021 paper, the Rooster paper is a new method for automated vetting of rotation periods. And you need a sample of well characterized, very well vetted rotation periods to train these kinds of things. We just need to be able to validate our TESS rotation periods somehow, and these existing catalogs are really important for that. So Timo Reinhold and Tyler Gordon, they have a couple of K2 rotation period catalogs. It's going to be really great for TESS rotation.
Cool. And George, how about you? Year 4.
Yeah, I'm really excited about the ecliptic mission. I think one of the main challenges for Planet people was the follow-up for the primary TESS and extended TESS mission, in that we only had about 2 months to follow up these targets before they set. And with the ecliptic mission, by laying TESS on its side, we get a lot more follow-up time for these for some of the fields. The other thing that I'm really excited for eventually when we get 200-second FFIs is the possibility of measuring all of these planets where the stellar modulation is almost at the same rate as the planet transit. And so that would be very exciting as well.
Cool. All right, one sentence answer from each of you. In 5 years' time, what's a question you want answered? And we'll go opposite order. George, what do you want to have? What do you want to know in 5 years?
Mass, radius, obliquity, period-age relationship.
Very, very concise. I appreciate it. Ruth, how about you?
So many, but one is I want to know the origin of the rotation period gap, the bimodal rotation period distribution of K&M dwarfs.
Great. Anne-Marie?
That's a very good question. I think, well, I'd just like to spend some time hammering down the mass dependence of young star variability and really have a good understanding of which phenomena we see at high mass and not at low mass and vice versa. And then what that actually tells us about inner disk structure and impacts for planet formation. That was a little bit of a long answer there.
There was a semicolon. It's still one sentence. It counts. Jason.
I'd like to have a clear view of all these different stellar structures. How big are they? Like how they actually formed and evolved over time.
All right. And one other question, another one sentence answer. The answer can be nothing. We've heard some plans for future tests, how cadences might change and gaps in the data. Is there anything, if you were George, and George, you have an advantage because your name is already George. If you were George Ricker, what would you want to change to maximize the science from young stars? Is there anything you would do differently for tests? Observing modes, fields, take your pick. If you want to just strictly maximize the science of young stars, how would you use tests if they handed you the keys?
So I think my prayers have already been answered with the 200-second FFIs. If at all possible, I would love to extend the all sky coverage and cover the gaps.
Great.
Oh, back to me.
Yeah, go ahead.
Well, George Ricker presented this idea of tests, another test at L5, and I'm not sure if the question got answered or not. I saw someone had asked in Slack whether it could have a slightly different bandpass. That would be awesome if we could have TESS L5 red or TESS L5 blue, and then we wouldn't have to rely on these ground-based observatories with more sparse time series to see what's going on with the color of the objects.
Wonderful. Ruth?
Somewhat controversially, I think one of the best things for rotation period studies would be more contiguous sectors for more stars, but that would limit all sky coverage, so it's a trade-off.
Yeah. And Jason?
I agree, but even if we can't extend the length of any sector, it's not really an imaginative solution, but just keep on doing what we're doing, and we'll have more and more opportunities to measure confidently rotation periods, because it doesn't always work out, but it could if we wait and do it again. I think we see that with Kepler and K2. As you wait to spot change patterns and amplitudes and periods become measurable because of the stars start cooperating.
Wonderful. I'm sorry to say we are at the end of our 50 minutes. I have so many questions for all of you that we didn't get to, but thank you for sitting and chatting for an hour. I think it was a great discussion. I learned a lot. I hope our listeners learned a lot. There's about 220 people here that listened to the panel. So thank you all for coming. I'll just mention to our panelists, we could not get to every question, of course. There's lots of great questions in the Slack. Many people tagged one or more of you in your questions, and so please look through, and if we didn't get to a question, go in and answer it if you can. And so let's all thank our speakers. Hold for applause, hold for applause. And I'll hand over to Jesse, who will be the chair for our next talks. So thank you, everyone.
Thanks very much, Ben.
Thanks, Ben. And thanks to all the panelists. All right, so now we have 2 more talks, sticking with the theme of youth. Then we're going to have a 10-minute break, and then we're going to split into 2 rooms. So for now, let's keep the questions in the Young Stars Slack channel. First up, we have Christopher Wirth, who's going to talk to us about mapping orbital obliquities of young star planets. So these talks are 12 minutes plus 3, Chris. So take it away. I see your screen.
Wonderful, thank you. All right.
And I hear you, so go ahead.
Okay, still see. Awesome.
Yeah,
All
yes,
right.
I still see it.
Thank you so much. Hello, everyone, and welcome. I hope everyone's enjoying the conference so far as much as I've been. My name is Chris Wirth, and I'm a rising junior at Harvard College studying astrophysics and physics. I'm so excited to continue talking about the incredible field of young exoplanet research with TESS, specifically through the lens of obliquities. So planet formation is believed to only last about 10 or so mega years, as that's the timescale for gas depletion around solar type stars. But that hardly means that the structure of a planetary system is set after that point, as dynamical evolution of the system can last until the stellar host is 100 mega years to even a gigayear old. And so we believe that a system's orbital obliquities can trace this dynamical history of the system. And so the orbital obliquity, or spin orbit angle, is the angle between the stellar spin axis and the planet's orbital axis. And so this cartoon I made shows possible formation pathways of a multi-planet system of Neptunes. And so we see Neptunes or super Earths around 30 to 50% of sun-like stars. So that's a really important demographic for us to be able to understand. So in the middle pathway, you can see our prevailing model for the formation of these systems. And so planets will form in situ in denser regions of the disk, and then migrate inwards through the disk to their observed locations. And so in our current models, this would lead to well-aligned warm Neptunes, which means a small obliquity angle. But as we can see in either the top or the bottom row, they could potentially be tilted by an external companion, either like in the top row where the companion could provide a torque on the planet-forming disk, and the planets would form in a tilted disk, or like in the bottom row where there would be a torque on the already formed system. And so both of these mechanisms would lead to a misaligned system or a large orbital obliquity angle. But since these mechanisms require some sort of companion, we would expect most Neptunes to be well aligned. So is that what we see? Let's take a look at all the planets with age and obliquity measurements, and let's just restrict it to before TESS for now. So we get a graph that looks like this. And so where would we would expect the Neptune-sized planets to be would be along this bottom area here, prograde orbits. And then polar planets will be in the middle and retrograde planets up at the top. So we can see a lot of misaligned planets, but these are all the planets. And so if we restrict this to planets smaller than 6 Earth radii, and we choose this number since young planets tend to be inflated, so that still sort of counts as Neptune sized. And so we get this for less than 6 Earth radius. So we see before TESS came into the picture, more misaligned small planets than well-aligned small planets. But since these types of planets are so abundant, if our current theories were to be correct, we would expect to see a lot of well-aligned small planets. So the question is, when and how did these systems get tilted? And do we just not have enough data? And so this is why young planets are so important, because we can see this huge gap to the left side of the graph, less than about 200 mega years or so. And so we don't have any idea what's going on there because we haven't observed any small young planets below 200 mega years. So without having knowledge of what's going on in this region, it's really difficult to answer these questions. So an interesting further question is, why before TESS came along did we have this gap? And so younger stars are more active, which makes it harder to find planets around them, especially smaller planets. And this has prevented ground-based surveys from really picking out these small young planets. And even K2 found a lot of young stars and a lot of young planets. They ended up being too dim for us to really follow up well. But with TESS and its all-sky photometric power, it's possible for us to pick out small young planets. For example, last year, TOI 942 was announced as a planet host by 2 different papers in the bottom right. And so while many young stars are identified as such by their membership in something like a young cluster, a young association, or a moving group, TOI 942 is a field star that was first picked out purely through TESS. So since young stars tend to be more active, they often exhibit this rotational variability we can see in the 2 sectors of TESS observations. So TESS data can be analyzed to pick out this characteristic shape, which I believe could be a really powerful tool to find more and more potential young stars in the future without having to rely on clusters or associations. So around this star, 2 transiting planets were identified. Test your exoplanet skills, see if you can pick out the transits by eye. 3, 2, 1. Here they are, one in pink and one in blue. So the inner planet TOI 942b is on about a 4-day orbit, and the outer planet TOI 942c is on a 10-day orbit, and they're both approximately Neptune-sized. So to confirm that this system is actually young, since more things than just a young star can lead to this rotational variability, spectroscopic measurements were obtained, and the discovery papers found a clear lithium signature, calcium HK emission, and X-ray emission, all of which combined for an age estimate centered around 60 million years old or so. So since most obliquity measurements had previously been of Jupiter-sized planets, and due to the scarcity of bright young planet hosts, even at 12th magnitude in the V-band, this system presented a good opportunity for follow-up. So to measure this obliquity and to perform the follow-up, we measured the obliquity of the inner planet TOI 942b, and we used the Roster-McLaughlin effect. And so this is when a transiting planet will obscure first the blue shifted and then the red shifted parts of a rotating star, or the opposite order, red shifted, then blue shifted, it's retrograde. And so when the planet goes in front of the blue shifted part, the star will look overall redder. And then when it goes in front of the red shifted part, the star will look overall bluer. And it'll produce this characteristic radial velocity signature that can be seen in the bottom panel. Let's watch it go by one more time. Beautiful animation by George. Okay, so to obtain these radial velocity measurements, we used the Planet Finder spectrograph on the Magellan telescope in Chile. And we observed 2 partial transits of TOI 942b, the inner planet, at the end of 2020. So immediately on looking at these observations in the second panel, you might notice it looks different from the animation, and the best fit model would confirm that suspicion. So the reason for this overall trend that we need to fit is because spots on the stellar surface move across on a much longer time scale and dim the star much more than the planet does. And so it'll cause this large scale variation in radial velocity measurements. But this isn't too much of a problem because it can be easily fit with a polynomial. But one thing we need to check is what happens if a planet goes across a spot? What does that do to the radial velocity? And so this model exaggerated to show the effect. We can see that if a planet goes across a huge spot, it'll cause this massive bump in the radial velocity curve. Again, this is exaggerated, so we just wanted to double check that this wouldn't end up affecting our measurement. So to test this, we modeled the spot distribution using the PFS spectral line profiles that we obtained for the radial velocities, and we found this on the left to be the best fit model. So modeling the RM effect with this spot distribution taken into account, we found that if a spot crossing event did occur, it would cause about a ½ meter per second bump in the radial velocities. If we go back here, we can see that the per point uncertainty on each of our measurements is way bigger than ½ meter per second. And so this was already accounted for in any error propagation that we had already done. And so with this check out of the way, we could be confident that the uncertainty was already accounted for, and we could detrend away the overall star spot effects. So this figure is the final nice looking detrended and phase folded radial velocity plot with a beautiful prograde Roster-McLaughlin effect. And so this effect is parameterized by the projected obliquity, but using what we know about the stellar rotation from TESS, we're able to derive the full 3D obliquity of TOI 942b using some basic geometry, and we find it to be totally prograde. So let's go back and remember what the less than 6 Earth radius distribution of age versus obliquity looked like before the TESS mission came along. Okay, what about now, about 3 years later? So using TESS's young planet finding abilities, we now have 3 planets younger than 100 megayears with obliquity measurements. And all of these are small and prograde. So here they are back again in context with all the larger planets. So drawing any conclusions now would probably be too early with only 3 data points. But as of this moment in time, we don't currently see any young misaligned planets. That's all I have, so I'd love to take any questions.
Thank you so much, Chris. All right, I'm going to ask the first question just on that last slide. So why don't we have obliquities for young giant planets? Like the top left of that plot seemed to not have much in it. Is that a selection effect or an observation effect, or do those planets not exist yet? Or
yeah, so we haven't So yeah, this is a selection effect. It's high, so we've highlighted, I think there are a few coming out soon, I think, but as of right now, the ones we have are small, which is interesting.
Okay. Yeah, I'd be curious to hear from observers why that is so, if anybody else wants to talk about that in the Slack. All right, let me check in the Slack if there are more questions. I see people typing. We have a minute. So my quick question while we're waiting for people to finish typing, TOI 942, you showed sectors, I think it was 5 and 32. Why was 32 so much noisier? Was that just a cadence difference?
Yes, that's just a cadence difference.
Okay, so it was put on a short cadence.
10 minute,
yeah. Okay. All right. I see Heis has asked a question. Heis Mulders, do you see trends between orbital period and misalignment?
So not really. What we would expect is for planets on a longer period to be to have a greater degree of scatter in that respect because of less tidal interactions. But again, since we have so few young planets, we can't really separate that from, we definitely don't have enough to see a big trend right now. With more young planets, we might be able to, that would be a really interesting thing to determine about when planets are young, if they get inclined. But since we have so few young planets, all the older ones kind of get messed up by tidal effects. And so I would expect that to be kind of confounded.
Okay, great. And then we'll sneak in one more from Yutanotsu. Are there any effects from the assumptions of star spot distributions or shapes when fitting the Roster-McLaughlin effects?
Yeah, so that's kind of what we tried to figure out here. And so, given that, once we get really powerful radio velocity tools, yes, that'll be a huge deal. But for right now, we could have chosen a very different configuration and the overall effect would still have been way below what we're able to determine for right now. So as of this moment, it's kind of just, you can just get rid of it with a polynomial and it won't mess up too much. But as precisions come in, we'll be able to precisions get better. We'll be able to, not just have to worry about it, but also learn some really cool stuff from it.
Right. So this 1 meter per second amplitude on these residuals, is that specific for TOI 942, or do you think that's pretty generic across young stars?
So this is just a toy. This is just like a toy model, just to test. Like we just made it cross and said, if it did this, we would this is the bump we would get. So I expect that to be relatively applicable to other stars, because of how contrived this was.
All right, thank you so much, Chris, for that talk. You have more questions in the chat, so please head there. Our next talk and the final talk of the first half of session 6 is from Nardiello Domenico, who is looking for planet candidates in young clusters and associations. So please take that away. We see it.
Okay, do you hear me?
And I hear you. Thank you so much.
Okay, thank you. Thank you for giving me the opportunity to talk about my project PATHOS. That is focused on the search of candidate exoplanets in stellar clusters and young association using TESS data. So let me introduce the problem that the project want to address with an example. This is a star, a well-famous star, hosting 5 planets. So it's a very amazing planetary system. But on the basis of the last works, this star has an age of about 6 gigayears, plus minus 4 gigayears. So within 1 sigma, 1.5 sigma, it could be very young or old. And this fact doesn't give us any information on the planetary status, on the evolution of this planetary system. Vice versa, if we look to stars in stellar clusters, we have stars that are formed from the same molecular cloud, are at the same distance, so are almost coeval and share also the same chemical properties. And the ages of these stars can be derived with extreme accuracy by using theoretical models or empirical approaches as like gyrochronology or isochrones. And not only the age suffer of small uncertainties, but also we can derive the stellar parameters of these stars with extreme accuracy, like the stellar radius, mass, effective temperature. And so the question why it's important to search for exoplanets in stellar clustering, association, streams, etc., is so important as a simple answer. If we look to these objects, we see they are all systems that are in the galaxy and have ages that goes from 5 megayears to 4 gigayears. And looking for exoplanets around the stars that belong to these systems means to have pictures of exoplanets at different ages, like the pictures of a person. We see how this person grows. And moreover, not only the age, so we can derive with extreme accuracy the age of these planets, but also deriving with extreme precision also the stellar characteristics, we can derive the planetary characteristics with the same precision. Anyway, there is a big problem, especially with the TESS images. We well know that the full frame images are low resolution images. And as you can see here, for an extreme case that is NGC 6791, looking to stellar cluster with TESS is look like to see an object without or with glasses. These are two examples. On the left, there is the TESS image. On the right, there is a ground-based image of the same object. And the crowding is a big problem. So even sparse stellar clusters appear like crowded environments, and contamination and dilution effects are a big problem to resolve. So for this reason, I developed a pipeline in the context of the PATHOS project that works well for long cadence, so full frame images, but also for short cadence data. And this pipeline includes an light curve extractor that make use of empirical PSF and neighbor subtraction. And the neighbor subtraction is the key to minimize the dilution effects. Here there is an example of eclipsing binary, a faint eclipsing binary of magnitude 14. It is a well-known eclipsing binary, and we can see the difference between before and after the neighbor subtraction in the transit, in the eclipsing depth. And also, so this pipeline allows us to extract the light curves, minimizing the dilution effects, but also to extract the real flux of the stars and the high precision light curves for very faint stars, up to TESS magnitude 15. And including the pipeline, there are light curves extracted with different photometric methods and homemade correction with co-trending basic vector. In the context of the exoplanets, the pipeline includes also the finding, betting, and modeling of the transiting objects. And let me show you some results obtained in the first 4 papers of the project PATHOS. We extracted and analyzed more than 376,000 light curves of 236,000 stars in open clusters and association, in more than 1,000 open clusters and association, finding 82 PATHOS objects of interest. For PATHOS object of interest, I mean objects that which light curves present transit signals and that pass the vetting test. 30 of these PATHOS objects of interest are good candidate exoplanets with a radius less than 2 Jupiter radii. And here you can see some example of candidate exoplanets that we found in stellar clustering and association, and the project is still going on, and thanks also to the new data from the TESS extended mission. So let me show some important results we obtained in the PATHOS project. First of all, the frequency of candidate exoplanets in open cluster. To derive them, we used this big formula that is a function of the planetary radius and the orbital period of the candidates, we estimated the false positive probability of the 30 candidate exoplanets, the FPP term, using the validation tool VESPA, and also the detection efficiency of our pipeline simulating different kind of exoplanets with different orbital periods. And on the left of this slide, you can see the detection efficiency for different interval of radii. And you can see that obviously for longer period planets, the detection efficiency is very low because the large part of the stars are observed in one or two sectors and only a small part in more than two sectors. But we expected that with the new data from the TESS extended mission, this detection efficiency will improve. So let me show the results we obtained. First of all, when the numerator of this formula is less than 1, we calculated the upper limit. Less than 1, it means that or we didn't have candidate exoplanets in the interval we're considering, or we had, for example, a 1 candidate exoplanet, but the false positive probability is larger than 0. And on average, we found that the upper limits, but also the frequency are lower than the values reported in literature in many works for the galactic field stars. And this is a very interesting result, but we are still working on this also in the optic to see if there is some dependency on the age, also thanks because we are analyzing also the new data to search for new candidates. And this is another important result we obtained during our project, and it is also the core of the PATHOS, of the project PATHOS, the evolution of the planets, or in this case of the planetary radius, as a function of the age. In this plot, we consider all the PATHOS objects, so all the candidates we have, and also the objects in literature that are candidate or confirmed exoplanets in a stellar cluster, association, or any system for which the age is well constrained. And if you see for radii less than 11 Earth radii, we see that there is a trend with the age. And the question is this trend a hint of the evolution of exoplanets? So we can see in detail this plot. Okay, as I said, for Earth radii larger than 11, so for Jupiter-sized candidates exoplanets, we have that the distribution is random, is randomly distributed between few megayears to 10 gigayears. If we look to objects with radii less than 4 Earth radii, so Earth, super-Earth, sub-Neptunes, we see that the points are concentrated at ages larger than 100 megayears. Anyway, this could be an observational bias due to the fact that that small size objects are difficult to detect for very young stars because of the activity. It is interesting the part of the plot between 4 and 11 Earth radii. In this case, all the points are concentrated below 100 megayears. Probably it is not a bias, observational bias, because we didn't expect. We expect to see also the points above this the 100 to 100 megayears, and it could be an evidence of planet evolution due, for example, this is only an example, but there are many other explanations due, for example, to the atmospheric escape due to photoevaporation, in which the planet in the first stages of its life inflated their atmosphere, capturing hydrogen and helium, and then lost this atmosphere because of the strong irradiation of the star. Okay, this is a very simplification of the models, and I apologize for it, but I have not so much time to explain everything. And so it could be an evidence of the planet evolution it could be, but obviously we need first of all a spectroscopy observation to confirm, but also photometric observation to confirm the candidate exoplanets, and then the masses of these objects. So let me conclude to showing an overview of the results we obtained in the project PATHOS outside the exoplanetary field. We also studied variable stars in different contexts. For example, the RGB stars in 47 TAC, that is a globular cluster, so being to studying an extreme case of crowding, and we found also a relation with the color and the magnitude of the branch of this globular class, of the RGB branch of this globular class. And also, we studied the variability of the young stars in the Young Association to derive the ages of this Young Association, this 5 Young Association. I'm leading a work on the geochronology of close by open clusters using the PATHOS liqueurs I used for the candidate exoplanets to derive the ages of these open clusters. I studied the dippers in T association to derive the properties of the dust in the circumstellar disk of these objects. Finally, don't miss the talk by Apai and collaborate by Apai regarding the couple of brown dwarfs Luhmann 16AB an analysis performed with the TESS curve, and also the talk by Mekares in the next session regarding the astrosysmology of giant stars in the CVZ. So that's all. You can find my PATHOS curves on the Mass Archive, and questions are welcome, also collaboration if you want, and any question also via email. Thank you very much.
Thank you so much. I have a ton of questions, but I see that there is some coming in the Slack already. Hi Smulders asks, the radius versus age trend in planet detection looks very interesting. Have you also calculated survey completeness or planet occurrence rates on these axes?
No. Yeah, it is a very good question. No, for now we are not completing this, also because the sample it is not so homogeneous. These are planets that come from different surveys. Some of them are from Kepler, some of them are from TESS. So regarding the entire, if we consider all the plot, no, the completeness is not calculated. While if we consider only the PATHOS project, but in this case we have only few points in the for small radii. Yes, it is the completeness of the pipe is associated to the completeness of the pipeline. So
thank you so much. There are more questions in the Slack, and I have more that I'm going to type in the Slack, but I don't want to go too much into our break time. So thank you so much again to the panelists and the speakers in this session. Thank you, Nardiello. Okay, Jen, I believe you have a slide to explain upcoming shenanigans with room splits.
I do. Thank you. Let me share that real quick. Share screen. Okay, so after the talk, we have our next set of parallel sessions. Folks who are interested in round 2 of exoplanets will stay right in this room, and Jesse will continue to be our chair for that. And then folks who are interested in the stellar astrophysics side of things, we will ask you to scoot over to, oh, I broke it. We'll ask you to scoot over to room number 2. There we go. Sorry about that. Where Jennifer Van Saders will be taking over chairing duties. And so 4 talks in each session. So it should be 1 more hour after the break. And after that, we are done for the day and we'll reconvene tomorrow morning.
Great. Thanks, Jen. All right. See everybody in about 9.5 minutes. Has everybody who wants to check their slides had a chance to check their slides?
Hi, Jesse, it's David. Could I, since I was late?
Yeah, go ahead.
All right, can you see my video at least?
We see you, yes. Hi.
Okay. Hey, good to see you. Like I have not seen you. Okay, can you see that?
Yes.
Okay.
It's a picture of Steve Howell.
It is. All right, but slides work.
Yep, that looks fine.
Okay.
Andrew, did you want to try yours?
Sure.
Okay. Yep, looks great.
Great.
Okay. And then Matthew and Ashley, I will play your videos from my computer. I will stop sharing after I play the video so that I can go to Slack so that everybody doesn't have to watch me check the Slack because that's where the questions are. So if the video disappears, that's why, because I have to stop the video so I can go to Slack. But then you should, unmute yourselves and be ready to answer questions.
Sure. Awesome. Thank you.
Sure,
No
yeah,
worries.
that's grand.
Okay. I just realized at some point I was like, oh, I can't do both of those things. I also just went and turned off my Slack notifications. I might just never turn them back on again.
I actually did that last night and missed a lot of messages because that's what I do instead of like going through each channel and like muting them. I just quit.
You're just done.
Yep.
Hey, Andrew, have you officially gone to MIT?
Yeah, I am in Boston now as of last week.
That's awesome. Congratulations.
Thank you. So my virtual background is hiding at lots of boxes.
Jesse, I just want to make sure all the speakers here.
I believe so. Yes.
Okay, just checking.
Yeah.
So at the hour, you can just take over, start the session. When it's over, wish everyone good night, good morning, and see you tomorrow.
Yep.
Okay.
Right. So Andrew, did you move to MIT? Did I miss something?
Yep, I just got here last week.
Okay. Didn't you just move somewhere else?
Yeah, I was in Wisconsin for a year.
I see. Okay.
And because it was COVID, I never actually went on campus. So a little bit weird, but I'm really excited.
Okay. Is it a faculty position at MIT?
Yep.
Yay. Exciting.
Yep.
Congratulations.
Thank you.
I love Boston. Boston's great.
Yeah, and I'll test all the time.
So Andrew, did you actually move from Texas to Wisconsin and then Wisconsin to Massachusetts all within the span of like 18 months?
Yep. It turns out
And
I
all
really
during a
didn't
pandemic.
need to be in Wisconsin physically. I did like go on walks with a few people occasionally from my group. But yeah, all of my teaching was online, so weird year. Hopefully this year will be more normal.
For all of us.
We'll see. I saw something about Delta Plus, which is like a worse Delta, and I was like, no, I can't. I'm out.
Okay, stop it, Jesse.
Peace out.
I think the weirdest bit for me this year was my oldest daughter got married in November, and it was a 10-person wedding in my backyard, 10 people, including the two women who were getting married. We all wore masks. There were no hugs or kisses, and the two families were on opposite sides of the yard. It was the strangest 3 hours.
Hopefully you get a chance to have a bigger, better party at some point.
Yeah, there's supposed to be, so not this November, but next November, they're doing a big actual wedding event.
Hooray. Okay, well, on that much nicer note, it's the top of the hour, so we can do the last hour of today. Thank you, everybody, for joining us for the exoplanet session. Exoplanets are number 1, so we're in room number 1. If you're expecting stellar talks, you need to go to room number 2. We have 4 talks this hour, 15 minutes each. We're going to kick off with Andrew Vanderburg, who's going to talk about planets around white dwarfs. All right, Andrew, floor's yours.
Thanks, Jesse. All right. Hi, everyone. I'm really excited to be able to talk to you today about looking for planets around white dwarfs using TESS. And I'm here on behalf of a large team of people who have made this work possible. So I want to thank all of them before I start. So as a bit of a change from what we were just talking about with young planets, I'm going to talk about old planets. And in particular, what I want to talk about is what happens to planetary systems after their stars run out of hydrogen, leave the main sequence, and die. And in particular, what happens to the planets that used to orbit around those stars, kind of like the ones in our solar system and like the most of the ones that we observe in our galaxy today. Almost all of the planets that we know about today that orbit stars in similar in mass to the sun or lower mass will eventually evolve into white dwarfs. So these planetary systems are going to change at some point in the future, and it'd be very interesting to know what's going to happen. So based on what we know about stellar evolution, probably what's going to happen in our own solar system is that when the sun runs out of nuclear fuel, it will puff up into a red giant, which is going to be about 200 times its current size. This will be very bad for the planets in the inner part of the solar system. Mercury, Venus, and Earth will all likely be engulfed. But the planets in the outer part of the solar system should survive this. So eventually, after all of the hydrogen fuel and all of the helium that's getting burned into heavier and heavier elements stops, and all of the fusion in the star stops, the sun will shed its outer layers. It will reveal its hot inner core, which is no longer fusing, but is still leftover, still warm from the leftover heat from its nuclear furnace in its previous life. And that will eventually cool into what we call a white dwarf. And as this happens, the star loses mass. So all of the orbits in the outer part of the solar system change and expand outwards. So we know that planets further out than about 1 AU from their stars will survive the post-main sequence evolution. This dividing line of about 1 AU is a little bit fuzzy, but if you're far enough away, in principle, you should be fine. And we've in fact seen planets orbiting white dwarf stars at very large distances. This is a direct image of a planetary mass companion around a white dwarf called WD 0806-661. And this is taken with Spitzer. And you can see that these two objects, this planet, which is about 8 Jupiter masses, and this white dwarf, are pretty far apart on the sky, but they're moving together with common proper motion. So you can tell that they're in a part of the same system. We've also seen that after the post-main sequence phase of evolution, small bodies from the outer part of the solar system, where they must have been in order to escape being engulfed earlier in their lifetime, can scatter inwards towards the white dwarf and be tidally disrupted. We've seen the evidence for this in these spectral lines on the surfaces of stars. We see evidence for heavy elements such as calcium in the spectra of white dwarfs, even though those elements shouldn't be there because the white dwarf's gravity is so strong that it should cause all of those elements to very rapidly sink towards the core and no longer show up in their spectra. And we've also seen transits of dust clouds around white dwarfs, including this one around the star WD 1145 plus 017. And most recently, we've found evidence of a giant planet close to a white dwarf. We've seen that there's a gaseous debris disk around a white dwarf and elements in the photosphere of this white dwarf that indicate that stuff is being removed from a giant planet. The composition of the debris is similar to the composition of ice giants in our own solar system. So we've seen all of this debris close to white dwarfs. The question that then begs is, if we know that planets can make this journey inwards close to white dwarfs and occasionally get disrupted because we see this debris, can planets sometimes survive this process as well? And to answer this question, we're using TESS. As we all know, TESS is awesome. It looks at lots of stars all across the sky. But one thing in particular makes it really well suited for looking at white dwarfs, even though white dwarfs are intrinsically faint. So TESS's small telescope apertures make it a little bit of a challenge. And that's the fact that TESS has a lot of slots for rapid observations. And these rapid observations, where we get 2-minute observations of selected targets, recently even 20-second observations of selected targets, and 10-minute cadence over the entire sky, make it possible to look for these very short duration transits of planets around white dwarfs. Because white dwarfs are very small, it does not take very long for an object to go in front of it, causing the transit duration to be very short, which means you need very fast observations like TESS can do to detect these transits. Here's an example of what I'm talking about. So on this top panel here, I'm showing the light curve of a particular white dwarf star. This is about a 17th magnitude white dwarf that is observed in 3 different modes, or has been binned to 3 different modes. Here's this white dwarf that's been binned to 30-minute cadence, which was what the original mission had for full frame images. Here's what it looks like binned to 10-minute cadence, which is what the current full frame image cadence is. And here's what it looks like binned to 2-minute cadence. In all 3 of these examples, I've injected a short duration planetary signal. But the signal is really only visible in the 2-minute cadence because the transit of this object is so fast going around the white dwarf. So if you want to find objects around white dwarfs, you need this fast cadence, and TESS is going to be great for that. And the extended mission number 2, where we'll have even faster cadence, will be really awesome. So we have a TESS program to observe thousands of white dwarfs all across the sky. We've identified white dwarfs using their HR diagram position from Gaia. We take advantage of a catalog that's been produced by Nicola Gentile Fusillo, sorry, I forgot, momentary lapse of the name. And we can take these objects in the HR diagram, identify them as white dwarfs based on their low luminosity. And then we can point TESS at these and ask for fast observations of up to 10,000 objects per cycle. We have about 10,000 objects that we're observing in cycle 4. So we're really excited to get these data. And you can take a look at Bob Aloisi's poster, who is a grad student working with me, who's looking for white dwarf planets in the full frame images. So in a complement to this program with the 2-minute cadence, we're looking in the full frame images. So we're looking all across the sky and all across the HR diagram, at least the white dwarf part of the HR diagram for these planets. So we have one detection of a possible planet around a white dwarf. This is the discovery light curve from TESS. And there's a couple of things to notice that make it likely that it's real. The first thing is that the planet has a very short duration transit. And as I just said, that's what we expect for white dwarfs. The duration of this transit is only about 8 minutes. And the other thing is it's relatively deep. White dwarfs are small, so you would expect for an object that is large as a planet, something the size of Earth, to cause a very deep dimming in brightness of this white dwarf, because white dwarfs and Earth-sized planets are fairly similar. So in this case, even though we see a 5% transit in the light curve, it's actually much deeper in reality. It turns out that when we take an observation with a large ground-based telescope, which has smaller pixel scale and higher spatial resolution than TESS, the depth of this transit is really about 56%. So this is a very deep transit. If we model this transit, it reveals that there is a Jupiter-sized companion around this white dwarf, but we don't really know anything else about it. We don't see necessarily any asymmetry in these transits, which would indicate that this planet is being ripped apart or is in any way disintegrating. So we think this must be an intact object. But we don't know necessarily what the mass of this object is based on this transit. That's a problem, because if you think about what the mass of something about the size of Jupiter can be, there's a large range of possible masses. Giant planets can have a radius of about 1 Jupiter radius, and their masses can range from about 1/4 of the mass of Jupiter to about 13 Jupiter masses. Anything larger in mass than that would be a brown dwarf, which still has a radius about the same size as Jupiter. And even low mass stars with masses between 80 and 120 Jupiter masses, or 0.1 roughly solar masses, still have a radius about the same size as Jupiter. So if we want to investigate this planet candidate and decide whether it's actually a planet, we have to figure out a way to measure its mass. Unfortunately, the way we usually measure the masses of planets is not possible in this case. Usually we look for changes in the radial velocity of a star by measuring the Doppler shift of spectral lines. Unfortunately, this white dwarf is old and cold, and as a result of this, has only a single weak spectral line, about a 3% deep H-alpha feature. So we can't make precise radial velocity measurements. We have to measure the mass another way. So instead, we observed this system with Spitzer and measured the depth of the transit at infrared wavelengths. Our logic is that if this planet is actually more massive than a planet, if it's a brown dwarf or if it's a star, then it should be glowing due to its own heat. And that glow should show up more strongly in Spitzer than it does in optical observations, because Spitzer is observing in the infrared. So if the depth of the transit is shallower in Spitzer, that's a sign that this planet is actually glowing and therefore must be too massive to be a planet. But that's not what we see. We see that this object has basically the same transit depth in the infrared as it does in the optical. And based on this and some modeling and using the known, the cooling models for brown dwarfs and giant planets, we can conclude that the mass has to be less than about 11 Jupiter masses at about 2 sigma confidence. So most likely this is actually a giant planet orbiting very close to a white dwarf star. So I wanted to leave you with this final thought. here's what the system looks like to scale. It's a little bit crazy to think about because this white dwarf is about 7 times smaller than the planet that it orbits. And the distance that this planet orbits from the white dwarf is similar to a typical hot Jupiter on the main sequence. But because the white dwarf is so low in luminosity, its habitable zone is actually not that far from the orbit of this planet. So even though white dwarfs are no longer producing their own heat, they are glowing enough that they could warm up a planet if it gets close enough in. And it's been a problem to imagine how a planet could make the journey close into a white dwarf and survive. But if WD-1856b, this Jupiter-sized object, could make the journey and get almost into the habitable zone of this white dwarf, then maybe a smaller rocky planet could too, which would open up the possibility for a second generation of life in a solar system after the star is long dead. And finally, white dwarfs are excellent targets for transmission spectroscopy. We've heard all about the small star opportunity, where the smaller your host star is, the larger your transit depths and the larger your atmospheric signals for transmission spectroscopy. White dwarfs take this to an extreme. So if there were an Earth-sized planet with an Earth-like atmosphere, it would be fairly easy to detect the atmosphere, and in particular, key biomarkers with James Webb in only about 25 observations. And because the transits of a white dwarf are so short, only about a minute for an Earth-sized planet, that means that you could potentially, with just about an hour of James Webb time, spread over many different transits and with a lot of overheads. To keep that in mind, with about an hour of James Webb time, you could detect key biomarkers such as water and oxygen and methane. So this could be a shortcut to identifying biosignatures. Using Gaia, we can identify white dwarfs. We can search them with transiting planets, or for transiting planets with TESS, especially with the new 200-second cadence that we're really excited about in Extended Mission 2. And if we find something, we could point at James Webb at it and try to learn what is in the atmosphere, perhaps faster than we'll be able to do this for stars around for planets around main sequence stars. So with that, I'll put up my conclusions, which are basically that TESS is awesome. We're using it to find planets around white dwarfs, and in the Extended Mission 2, 200-second FFIs will be awesome. We found one planet candidate, which is almost certainly a giant planet, lower likelihood. It's a very low mass brown dwarf, and we just got a little bit unlucky with the statistics. And this demonstrates that low mass objects can survive migration close to white dwarfs. And if Earth-sized planets migrate in a similar way to how this object got there, then they could potentially end up orbiting close to the white dwarf's habitable zone and could be a place where you might want to look for a second generation of life in a solar system. And I'll take questions. Thank you.
Thank you, Andrew. Okay, the first few questions actually match one of the questions I wrote down, which is about this grazing orientation of this giant planet around this white dwarf. You know, how lucky is it that you got this instead of a full occultation, and what does that mean for how many were missed? And also, since it's grazing, how difficult was it to work out, like, the architecture, the size versus the inclination and stuff?
Yeah, that's a great question. So in terms of how likely it is to find a grazing system like this, in this case, the impact parameter of this planet is about 7. And if you think about where you will find a grazing transit versus where you'll find a complete transit, you'll find a complete transit with impact parameters from about 0 to 6, and you'll have a grazing transit from impact parameters of about 6 to 8. So that's about a 1 in 4 chance that any random planet transiting a white dwarf would have a grazing transit instead of a 100% deep transit. That actually helps us in this case because it means that it'll be easier to get atmospheric measurements, because you'll have more time when the limb of the atmosphere is actually being illuminated by the white dwarf. And I forgot the second part of the question. Can you say that
The other
again?
half of the question was, how did you break the degeneracy between impact inclination and size of the object?
Right, yeah. So to do that, you need to impose a prior on the stellar density. And if you don't do that, then you have essentially a hopeless degeneracy. But because we believe that the orbit should have circularized very quickly, and we can put this prior on the density of the white dwarf because we think we understand white dwarf mass radius relationship fairly well, perhaps not perfectly, we can get a pretty good constraint on what the radius of this object is.
Okay, great. Thank you so much. There's more questions. I have more questions. So please go to the Slack and help people with those. Our next speaker is Matthew Battley, who's going to talk about revisiting the Kepler field with TESS. So Matthew has sent me a talk. So I'm going to play the recording. Any technical difficulties are on me, not on Matthew. Please put your questions in the exoplanets channel and we'll get to them at the end. So I'm going to share Matthew's video. I'm going to tuck it away from all of the are you seeing Ashley's or Matthew's?
It's a gray screen at the moment, Jesse.
All right, let's try it again. We had some shenanigans with this before, but we did get it to work. Matthew optimized. Here, I'll put Ashley's away. All right, are you seeing it now?
Yes.
Great. Does it have any gray bars on it?
No, that looks good.
Fantastic. Then I will play, interrupt if there's no sound in about 10 seconds.
Working under the supervision
of Don
Delaco.
Go back to the start. Try again. Okay.
Hi everyone, I'm Matthew Battley, a third-year PhD student at the University of Warwick, working under the supervision of Don Delaco. Today I'm excited to share with you how TESS is extending the legacy of the Kepler Space Telescope with re-observations of the Kepler field in TESS's primary mission. As I'm sure I don't need to belabor here, the Kepler Space Telescope proved to be transformational on our field, showing a previously unseen breadth and depth of exoplanets in a relatively small area of the sky. Among many other things, Kepler told us that planets outnumber stars, small planets are common, and our solar system is by no means the archetypical planetary system. However, with the failure of two of the telescope's reaction wheels in 2013, Kepler was no longer stable enough to focus on the same field, and instead switched to the still very successful K2 program. This unfortunately left the bulk of the Kepler field out in the dark, with some very interesting objects going unobserved for almost 7 years. Thankfully, TESS has now come to the rescue for these exoplanets, revisiting the entire Kepler field in year 2 of its primary mission, and truly taking on the planet hunting torch. Now, obviously, the Kepler and TESS missions were designed with quite different primary missions in mind, and TESS is most sensitive to the brighter, larger, short period exoplanets seen by Kepler. Nonetheless, in 2018, Kreis, Monte, and Fabricki modeled that 277 Kepler planets had a greater than 50% chance of being reobserved with TESS in a single sector, with about 150 more in 2 sectors, as you can see on the plot on the left. Similarly, with Kepler finding many interesting multi-planet systems, Goldberg et al. Estimated that the short 2-minute cadence data collected by TESS could improve the TDV mass uncertainty for 6 to 14 planets in TESS's primary mission. Following the launch of TESS, Ecuador et al. Demonstrated the excellent performance of combining TESS and Kepler data for 4 K2 planets, reducing the uncertainty in planetary period for K214b in particular by a factor of 66. These promising results motivated our analysis of the entire Kepler field, focusing on those which received short cadence 2-minute observations. TESS reobserved the Kepler field in year 2 of its primary mission, primarily in sector 14, but also partially in sectors 15 and 26, which you can see on the right. Of these, 962 stars received 2-minute data, including on the order of 50 planet hosts and 30 sister rings, potentially harboring planet candidates. However, just because a star received 2-minute data does not necessarily mean that we can see a planet signal on it. Indeed, there are 2 main challenges to recovering these: signal to noise and timing. This is my favorite example of the timing challenge. Shown here is a combined sector 14 to 15 light curve of tick 271881482, around which the planet candidate KOI 974.01 orbits. It is a period of about 53.5 days, so you'd hope that you'd pick up 1 transit in 2 sectors. And indeed we should, if there wasn't an incredibly timed period of excess scattered noise just in that middle of sector 14, which unfortunately had to be removed. We checked within this data cut just in case. The scattered light completely overwhelmed any potential signal. You can rest assured that plenty more transits fell perfectly in one of those TESS data gaps as well, especially given the long period of many Kepler planets. It is worth noting, however, that even if that section hadn't suffered from excess scattered noise, scattered light, that is, we may have still struggled to see the 2.5 Earth radius planet due to the second main challenge, which is noise. The differences in TESS and Kepler photometry are the most striking in a side-by-side comparison like this. As we can see here, the statistical noise in the TESS light curves on the right is considerably larger than it is in the Kepler light curves on the left. This is only natural, given the much smaller effective lens size of the TESS telescopes, but still surprised us in a direct comparison. This means that while hot Jupiters like HAP B7b on the top are clearly seen, small planets, such as the super-Earth Kepler 21b, are unfortunately completely lost in the noise. This noise, coupled with the relatively short windows of the TESS observations, meant that only 22 of the 93 Kepler planets and 4 of the 28 candidates had transits with sufficient signal to allow their ephemerides to be updated using the TESS data. But if you're interested in a specific object of those 93, information detailing the inclusion or removal of each of these objects and planets can be found in the appendix of our recent paper, Battley et al. 2021. Nonetheless, for those planets and candidates with sufficient signal to noise, TESS provided a superb data set to revisit these systems, often some 7 years after their last observations, as I mentioned before. We used an iterative approach to get up-to-date transit times for each system, beginning with Batman transit models based on the most up-to-date planet parameters in the literature, before using those to search for individual transits and build an overall stack model. The exoplanet package's inbuilt optimize routine was then used to hone in on precise transit times, which we used in turn to build O-C diagrams for each object and update planet ephemerides. Overall, we updated and improved the ephemerides for 22 planets and 4 candidates, significantly decreasing the timing uncertainty for many, especially candidates, and bringing them to the present rather than 7 years out of date. It should be noted that while some multi-planet systems, only a single planet was able to be recovered due to timing noise challenges for smaller planets. Often you might see, for example, only planet D was recovered when B and SME are much smaller. The O-C diagrams also proved quite instructive, with over half of the systems examined here showing evidence of transit timing variations, or TTVs, some of which we'll look into now. Firstly, something quite surprising can be seen for the well-studied hot Jupiter HAP P7b. Although the TESS error bars are much larger than the Kepler ones, there is a hint of a shift of about 2.5 minutes in the positive O-C direction for the TESS transits, especially if one combines all of them. It should be noted that a similar shift was seen in the discovery paper in 2008 by Parr. We await new data from TESS to see if this continues in later years. Secondly, large-scale TTVs can still be seen to continue for Kepler 396b and c, although only 1 to 2 new transits were present in the TESS data. This is particularly obvious in 396c, which has that single transit point up in the top right. Motivated by Goldberg et al.'s forecast for multi-planet systems, TTV fits were attempted for this system, along with Kepler 18, Kepler 25, Kepler 51, and Kepler 89. But given that only often 1 to 2 transits fell within the TESS observations, more TESS transits would be beneficial before significant mass updates can be made. As you can see here, especially as you can see here, the TESS error bars are much larger than those Kepler ones. The Kepler 18 and KOI 13 systems were also interesting, with Kepler 18d the only planet in its system which was recovered, as both planets B and C were unfortunately too shallow in the TESS data. KOI 13b, on the other hand, also known as Kepler 13ab, was one of the objects that received the most new data in TESS's primary mission, being observed in sectors 14, 15, and 26. This object was one of those highlighted as being most useful for monitoring tidal decay, but no evidence of this effect was seen here, as has been corroborated by Sabo et al. Interesting results were also seen for the 4 Kepler candidates updated in this study. First of all, the increased cadence of the TESS 2-minute data allowed us to more clearly see the nature of K00971, which now appears to be a false positive due to fast variability. Meanwhile, large continued TDVs are clear in both K00075 and K00076.01, which look like fascinating systems to further analyze and hopefully confirm as data continues to come in from TESS. All of these results show that TESS is crucial not only as a planet finder in its own right, but also an incredibly powerful exoplanet follow-up instrument. This bodes well for the continuing TESS extended mission, which will return to the Kepler field in year 4. The future is bright for further analysis of Kepler objects, both because future observations are likely to catch some of those missed in this first viewing, and because there are many more we can update in a wider study, the full-frame images, which we recommend for further studies. Furthermore, it is clear that these multi-planet systems have much more to offer in the way of transit time and variations. So continuing to observe the Kepler field as the TESS extended mission continues will no doubt continue to give us interesting scientific results. So to conclude, TESS is once again shining a light on some of the most fascinating discoveries made by Kepler and extending the life of some really important exoplanetary systems. We have updated the ephemerides for 22 Kepler planets and 4 Kepler candidates, representing all of those with sufficient signal-to-noise and a short cadence data for the TESS primary mission. Future observations of the Kepler field and further analysis of the TESS FFIs are bound to provide further important scientific return. And with that, I'm happy to take any questions. Thanks.
All right. Okay. Matt, you're there. Great. Let me check how we're doing. Okay, there are questions. Brian Jackson, I'm excited about your HAT P7 TTV result. Is it consistent with period decay? I was also excited about the HAT P7 result because, that's a very well studied hot Jupiter. And, I would have thought that there would be limits on companions in that system. So tell us about HAT P7.
Yeah, so we were really surprised by that as well. It seemed that it was quite well constrained from the Kepler data alone, and so seeing that shift there consistently was really quite odd. But if you average all of those test data points, it is quite a clear shift above. And unfortunately, there aren't very many well constrained data points between the Kepler ones about 7 years ago and TESS there as well. And the best constrained one before those Kepler ones, obviously the Discovery paper, but that's now about 12 years ago.
And epoxy got some good transits of HAT P7.
Absolutely, yeah. No, so there are some nice ones in between the gaps here as well. But from what we can tell, there does seem to be an ever so slight sort of U shape as we saw on the plot there before.
That's really interesting.
Yeah. So hopefully that'll continue with TESS.
Right. Okay, James Jackman asks, could you use your results to estimate how many multi-planet systems seen with TESS might only appear as single systems from photometry alone?
So, but just thinking about, I'm not sure I entirely understand what.
Sure, so you're looking at Kepler multi-planet systems and you're only recovering like one planet. Can you infer from that, given the TESS detections, how many of those might be multi-planet systems? Given the incompleteness we can infer from what you're seeing on the TESS data on the Kepler systems.
Oh yeah, so it's a great question. I think where it will be really important is probably those continued transit timing variations, and if they're good enough on the on say one of the 3 planets we catch, then certainly we could model those and infer any continued mass measurements from that. But I think the trouble is currently we've only got 1 to 2 data points, as we said, and so we probably can't constrain things any further at this stage. The hope would be, especially as we go to start to revisit these things in future years, we'll get again more of that long, not duration, but just long period to start looking over things. That's going to be particularly important, I think, for the candidates, which still have relatively few things so far. And so I think if we can pick up a few more transits of those, we'll really start to be probing things nicely.
Right. I'm going to sneak in one more question. So there's a lot of concern for future missions like Ariel about ephemerides getting stale, from observations that were taken years ago and projecting forward. With these updated ephemerides, did you find any significant offsets? Like, were there any cases where that transit would have been lost if you had propagated 5 years in the future and just gone where you thought it was going to be?
So that is very much the case for the some of the KOIs, because a few of those, because they're relatively long period, actually only had 8 or so transits in the past, or sometimes fewer. And so certainly every one of those we found new ones of, like we've found for some of those K2 planets as well, had a significantly improved effect. So of course, some of the hot Jupiters and the really short period ones are less affected, but I think it's really the candidates that we need to keep doing these updates for.
Okay. Thank you again, Matthew.
Cheers.
All right. Our next talk is another recorded talk that Ashley Chontos has sent me. She's presenting a homogeneous population of test planets orbiting subgiants. So once again, I will attempt to share my screen. This is all going to go flawlessly, I'm sure. All right. Share screen, optimized for video. Ashley's player. Okay. Can you see Ashley's screen with no gray bars on top?
There's a tiny one at the very, oh no, and it's gone now. I think you're good.
Right, great. And I will play, and Ashley, at the end, I will stop sharing and we'll take questions.
Sounds great, thank you. Hello everyone, I have so much to talk about, so I'm just gonna jump right in. Before I can talk about the planets that I've been following up over the last couple of years, I would like to first introduce the survey that made the study possible, which is TKS, or the TESS survey, or TKS. We heard a great talk yesterday by another TKS graduate student, Joey Murphy at UC Santa Cruz, but very briefly, in case you were not there or did not get a chance to see his talk yet, TKS is a very large collaboration amongst partner Keck institutions. Collectively, we were awarded more than 100 nights over 4 semesters using high-res on Keck 1 telescope to confirm and characterize test planets. Now, in terms of science, we have already collected a number of single system publications at various stages in their lives. A lot of our earlier work, TKS 1 through 4, has already been accepted and published. As Joey pointed out in his talk, there are a lot of numbers missing between 4 and 10, but I can assure you they're not missing, they're just going through the process. And then finally, we do have some still in their earlier stages. In fact, for this special system, TUI 1246, another TKS grad student, Emma Turtleboom at UC Berkeley, is presenting a beautiful poster on this system, so I'll let you go visit her and she can tell you why it's awesome. But now for ensemble catalogs, it's a bit of a different story. For starters, it's still early, and we all know that catalogs take a lot of energy and time. But also a lot of the catalog level products from TKS are being led by more junior scientists within the collaboration. A perfect example is Joey Murphy, who we saw yesterday, is talking about, now I went backwards, about population level atmospheric prospects. However, I am pleased to say that we recently submitted our first in the series of ensemble analyses, or the 0th paper out of the survey. As you can see by the title, this lays out the science motivations for TKS and ultimately why we selected the sample that we did. But because this is a TESS science conference, people want to hear about science. I'm not going to bore you with the vetting and selection steps, but refer you to the paper if you want some clarifications there. The one thing I did want to point out is that the paper highlights the importance of reproducible populations, with a particular emphasis on RV surveys, since this has been a major limitation for exoplanet demographics. So often we might drop a target that has a stellar, substellar companion, rapid rotation, high activity levels that would require GP processing to disentangle the signal. Of course, this is fine, but it's made survey selection functions extremely difficult to reproduce in later studies. So anyway, we came up with this idea for an algorithm. We implemented it, and how did we do? So this figure's showing a lot. I'll break it down for you. The top 2 panels are stellar properties. The bottom 2 panels are planet properties. The top left is an HR diagram. The top right is in stellar mass metallicity space. And then the bottom 2 are the planet size on the y-axis, and then period and incident flux space on the x-axis. So we started with a fully observable TOI sample in gray. TOIs for which we grabbed a recon spectrum and it passed all of our various vetting and selection steps is shown in black. So specifically, these targets were available during the target selection process. And then finally, we have our selected sample shown in orange. So what is this saying? Well, even with 100 nights, we still wouldn't be able to go out and measure awesome masses for all of these targets. But that doesn't mean that they're not great targets. So I'm hoping the paper could be used as a reference to identify other promising targets that might hit more specific science interests or something just not directly related to TKS at all. So Joey briefly discussed this yesterday, but TKS is broken down into 4 main science themes. So now let's take a look at only the TKS sample, split up by its 4 science themes over the same parameter spaces. So concentric rings demonstrate targets that were selected by multiple programs. And if we look at the numbers, you can see there is an enormous amount of overlap between 3 of the 4 main science cases. So as I previously alluded to, we implemented a unique algorithm to strategically select the optimal target sample given the various science goals and telescope allocations. And this is a beautiful demonstration, rather proof of concept, of the unique target selection that we implemented. So now for the rest of my talk, I will be focusing on this guy over here, which has essentially little to no overlap with the rest of the TKS targets, and you can visually see that it's an outlier in many parameter spaces. But to start with some motivation, I wanted to show this great figure from a 2018 review by Rebecca Dawson and John Johnson discussing the origin of hot Jupiters, one of the first ever planet types to be discovered, and it still stumps us to this day. Where did they come from? How did they get there? And in particular, I really like this table because it synthesized all of the information, literally decades worth of work, into a single table. So the table columns have the 3 main popular hypotheses of hot Jupiter formation, which is in situ formation, ex situ formation and migration, inward migration, disk migration, and then high eccentricity or tidal migration. You can see that some of them, they each have their strengths and weaknesses, but caveat is that there's no single great answer for the entire observed population of hot Jupiters. And one of the main takeaways from this table, or at least what I took out of this, is that stellar ages might help here. And this is where our program comes in. So the subgiant branch is a rapid phase in stellar evolution. So a location on an HR diagram gives us a really precise, not only age, but also mass, which is really helpful for characterizing these systems. But because they're more evolved or a little bit larger, we'll also be biased towards larger planets, so that actually might help inform some of these theories. But to test our hypothesis, we characterized all the TOIs using isoclassify to determine their ages, and I plotted the histograms of the fractional age uncertainties, I think up through TOI 2500. This was done a little bit ago. So not unexpectedly, we see fractional age uncertainties all over the place, but if we strictly limit it to the stars in our sample, you can see it looks much better. So that was a great sanity check. So anyways, enough about the ages. What does the sample look like? So here's the program sample in an HR diagram on the left and planet radius incident flux space on the right. Markers are colored by their mass significance. What I mean by this is the darker the marker, basically the better the mass. And then additional planets that we found as part of this survey, they're not TOIs, non-transiting, are shown in orange. And for these, I just used a basic mass radius relation to get a rough planet radius, but I'll show the masses later. Now, mind you, keep in mind, I have more planets than time to highlight, so I'm going to zip through some of my favorites at the moment. I'd like to emphasize that there are also a lot of other fascinating systems in the sample. So for each of these systems, I will highlight them on the population level, show our current data for this system, and then highlight some of the unique characteristics. And the first is my personal favorite, TOI 2145. Right away, you can see the star is quite massive and young-ish. In fact, it's pretty metal rich, so it's even more massive than the solar tracks that I have there for reference let on. Now the planet is also enormously massive. I was about to call it a hot Jupiter, but then I just realized it's technically, I guess, falls in the warm Jupiter regime. Regardless, close and massive planets around massive stars are incredibly rare. Not only that, but there is also a probable close planetary companion, and you can see that in the fit and near a 2-to-1 resonance there. So I'm still trying to wrap my head around this. But moving on, the next TOI I'll talk about is TOI 1736. This one is much older than the previous one, actually an older solar-ish like star. I keep saying ish. So the system initially confounded me because there were a lot of TCE and DV reports generated for this small transiting planet candidate, but I noticed they all had roughly the same period. So the obvious thing to me was like, oh, is this a TTV system? I showed it to others in TKS and everything seemed to check out. So we just decided to follow it up. Lo and behold, there's a massive outer companion where we managed to get peri-passage thanks to the Automated Planet Finder, APF, but we're still trying to nail down the period. And it's also worth noting that there are a lot of periodicity present in the residual time series data. I don't know if this TTV systems are not really my jam, so I don't know if this is common, but regardless, it's a super interesting system. Okay, so we've had our hot, warm super Jupiter, a cold super Jupiter. Now let's switch to an eccentric hot Jupiter. This is also an older solar-like star, but here we have a significantly eccentric hot Jupiter. As you can see, there is a significant trend here, but it's definitely not as well fleshed out. But it's still quite interesting given the eccentric hot Jupiter. And I don't want to spend too much time here because I still have one more system to highlight and I'm running out of time. So TOI 1898 is actually a funny story. You can see that early on in the time series, it's actually being followed up with APF, courtesy of Paul Dalba, a postdoc, a TCAS postdoc who's been working a lot with the single transiting planet candidates. At the time, I didn't know this, and I started also following it up with HiRes, and then we just were like, hey, we're both following up the same thing, and the two together, which kind of saved the day and rescued the period for the single transiting candidate. However, I don't know if you see this, but something else is going on in the residual fits where you can, I don't know, I've just highlighted a few points. It just wasn't adding up. And I thought we were getting the period wrong because we only did have the one transit. However, when we injected another planet, it seemed to do a pretty good job describing the system. And because of the extended baseline and additional phase coverage the APF gave us, we were able to get a 3 sigma mass constraint on the planet that's at roughly 2 times the period of the inner. So this one was interesting to me because eccentric warm Jupiters are good for high eccentricity migration theories, but the somewhat close companion is not. And the opposite is true for the in situ formation or ex situ formation migration scenario, at least with one having a significantly non-zero eccentricity. So anyway, we still need more observations. We have this wonderful sample of planetary systems that come in all different shapes and sizes. We have stellar ages, we have precise stellar ages, we have a wide range of stellar masses, and the idea is that first we'll compare these to main sequence and red giant planet populations, but also because we have such a nice diversity of systems with large planets, we can revisit things like what I had discussed earlier about hot Jupiter formation and migration, and maybe even tie in those ages to better constrain some of the dynamical timescales over which these processes occur. The one thing I did want to say is the unique thing about our program is that we aren't just following these up for confirmation, we are continuing to follow these up today. So we're probing long-term characteristics in these systems, therefore sensitive to the eccentricities in the systems, simplicities of the systems. So stay tuned. I'm currently working on the catalog paper, and with that, I will leave up the figure from my TCAS Evolve. Oh yeah, again, we have more fun systems in there and some small ones too. As I said before, I encourage everyone to check out the TKS paper. And then finally, I will shamelessly use this space as a plugin for something completely unrelated, since this is precisely the type of audience we would hope will use it, which is new open source astroseismology that hit the archive yesterday. And the code was calibrated with wonderful space-based photometry missions like TESS, so it's already ready to go. Please see me if you have any questions about that. Thank you so much. Sorry for going over on time.
Okay, great. Thank you, Ashley. You even acknowledged in the video that you went a little bit long. That's okay. Let me
It's
see.
so hard.
Okay, you need to go into the Slack and talk about cats, but let's get the question from Chris. Nice detective story with the TOI 18 one. Any AO imaging follow-up on those systems with RV trends?
I'm sorry, say the system name again?
They didn't quite catch it in the Slack. The Slack says TOI 18 something.
Okay. 18.
There was a longer trend, I think. And have you done
16
AO
over
imaging?
5. Okay. Okay, so they're saying they do have imaging for it.
They're asking if you have imaging for it.
Ooh. We were collaborating with I believe another team is following this up. I want to say led by Joey Rodriguez. I'm not totally sure if I'm remembering this correctly, but I think there might be AO imaging available for this one that we have not looked into yet.
Okay.
Yeah.
Right. I will quickly add a question. So you're looking at evolved stars that have TOIs. Did you particularly choose the eccentric ones to show us, or is it turning out that lots of these TOIs around evolved stars are eccentric?
Yes. Well, actually, so yes, you're onto something very interesting, which is what we're also really interested in as well. I mean, there are, I guess I did kind of show the ones with more eccentric orbits, but the selection effects were actually just like, I didn't require any sort of parameters, periods, planet sizes, or anything. These were just what turned out to be the sample, and it just so happened to span like a nice diversity of planet parameters. But the eccentricities are definitely something that we are interested in because a lot of these we would have expected to already circularize, which is what we plan on doing with the ages. And because they're subgiants, we can trace them really well back to like their 0 age mean sequence information and try to like trace out what this system has been like, kind of how it's been evolving.
Right. Well, it'll be interesting to see if that pans out. So we'll look forward to your next talk. Thank you so much again.
Thank you.
Okay, the final talk in our session is David Ciardi, who is not giving a recorded talk. He's just going to share his slides, so I can't break it in any way. Hooray! And David's going to tell us what have we learned about exoplanet host stars. Thank you, David.
Okay, can you guys hear me and see my slides?
Yes.
Okay, thank you, everybody. So just quickly, this talk was originally submitted by Steve Howell, and I just wanted to, he couldn't make the talk today, so I'm stepping in to give it for him. But it is a collaborative effort amongst Steve and a whole group of us that are listed here, including myself. And so towards that end, I just wanted to say thank you to the SOC for allowing us to present this program. So as you all know, planet radii are derived from the transit depths. And in particular, you measure the transit depth, but you need to also know what the stellar radius is in order to derive the planetary radius. But it's not always that clear because, if I can advance my slide, because sometimes it's more complicated that there are other stars either bound or along the line of sight that influence what the observed transit looks like. And so if there's another star, you not only have to take into account the flux of the primary star, but you also have to take into account the flux of the contaminating star. And you also have to pay attention to which star do you think that the planet is actually transiting. And it's particularly important for bound stellar companions as opposed to simply line of sight stellar companions. And so there are two possibilities. Not only do you have to take into account the flux contamination, so if the planet is orbiting the primary star, if the stars are nearly equal brightness, then you end up with a flux contamination of about a factor of 1.4 square root of 2, which asymptotically approaches a correction of unity as the secondary star gets fainter and fainter and fainter. But if the planet orbits the secondary star, then it means that you're transiting, the radius of the star that you're transiting could be very different. And so your planet radius could be wrong, not only by a factor of about 1.4, but by a factor of a few. And here's a really fun example that actually comes out of the Kepler field originally, but this is Kepler 1002. You can see there are two very bright stars next to each other. So SG1 is all about separating out which star the transit might be around. So this is what TESS looks like for these two stars, and SG1 is all about figuring out, okay, the transit is around this star, but high resolution imaging reveals that this star itself is actually a ½ arcsecond binary. And so in the original assumption of the star being single, we thought that this planet was about the size of 1.5 our Earth, making it a rocky planet, and it would show up here in the radius distribution on the rocky side of the period of the radius gap. But once you take into account that it's a binary and you do the deblending, that planet either falls directly into the gap if it orbits the primary, or it's way outside the gap and is much more Neptune-like if it orbits the secondary star. And so the goal here is to try to characterize the binarity of systems, and understand the planet radii at a much higher level. And it turns out that I wrote this paper a long time ago now, that if you do nothing, if you know nothing about the multiplicity of the star and you just assume it's single, then just statistically, you end up underestimating the planet radius by a factor of 1.5. And so while the radius might not be wrong, that is, the star might indeed be single, you've added this extra uncertainty onto your planet radius, which really goes unaccounted for in most papers, unless you actually do the multiplicity study. So we have a program where we're trying to survey as many, if not all, of the TESS candidate host stars. And it's a community service program where we're putting together a variety of programs on Gemini, on WIN, on Palomar, on Keck, and making all of that data and analysis publicly available through the exofile to the community with no exclusive use period. And so actually, while Ashley was talking in the previous talk, I went and looked, and sure enough, Ashley, we've done a whole bunch of your targets. So they do have AO, and if you need more, just let us know, and we'll continue to do them for you specifically. So this is the next few slides. I'm going to present a bit of the actual science that we're doing based on the observations from this program that we're doing for the community. So the first part of the program is with our optical speckle cameras. They are on WIN, which is a 3.5 meter telescope in Nessie, but they're also on Gemini North and Gemini South, the 8 meter telescopes Alapeke and Zorro. And in addition to our program, there's full community access through the normal NUAR Lab proposal process for these programs. And there's other programs that use these cameras in addition to ourselves. The good part about these two cameras, especially on Gemini, is that you get two simultaneous filters at the same time. So we typically do something like 0.55 microns and 0.83 microns at the same time. And because this is an optical and these are on 8 meter telescopes, the resolution is pretty exquisite. We can get down to about 0.01 arcseconds at the shorter wavelengths on the 8 meter telescopes. And our typical sensitivities are sufficient to get down through most of the main sequence on most G, K, and M stars. The other set of facilities that we're using complement the optical speckle cameras. They are near-infrared adaptive optics, primarily on Palomar and Keck. And one of the nice things about Keck is that it has a laser guide star system if you want to go to some of the fainter stars, which are often hard to get when you're doing natural guide star observations, especially for the fainter M stars. Faro on Palomar is behind a new AO system, and so we're actually able to reach fairly far down into the M star sequence for the TESS candidates. And Keck, of course, has full community access through NASA time. Palomar is a private institution, but there are ways to work with us and write proposals if there are specific things that you want to do. But the really nice part is that the near IR complements the optical because it's slightly more sensitive, or is more sensitive to the lower main sequence, and the resolutions are comparable to the longer wavelengths on the larger telescopes. So what have we found so far? So we've done approximately 500 targets, and we're finding a series of exoplanet host binaries. The higher resolution with the optical speckle observations allow us to go further in, and the deeper sensitivity of the infrared allow us to go down further in the main sequence, and they allow us to complement the observations. But it's also important to understand what it is that you don't detect. So there's lots of, we're detecting binaries, and we mark those and let people know that, hey, your system has a binary system. But it's also important to understand what stars are you missing. And so without too much of a surprise, right, that the better your resolution, the better that you can get further into the binary companion distribution, and the greater percentage of companions that you are likely to detect. And as your resolution degrades, because either the star is further away, or because your telescope is smaller, or because you're using a longer wavelength, then your fraction of companions that you're likely to detect goes down. But I would like to point out that overall, our program detects, is expected to detect at least half of the expected binaries. And for most of the targets, because TESS stars are so close, that we're able to detect 70 to 90% of the stellar companions. You can also see that there's a mass dependency here. The higher mass stars, we are less efficient in being able to detect their companions. And that's a result of A stars and F stars can have companions which are mid to late M's, and those are significantly fainter, and so they become harder to detect. But the point of this slide is not just that we're reporting what we find, we're also able to characterize what we don't find. And so we've taken the binary detections that we found, and we've written a paper. These two graphs are based mostly on our Gemini and WIN speckle observations, with a paper by Katie Lester, which actually just got accepted, I think, last month. And one of the things I'd like to point out is that the mass ratio distribution of the companion to the primary looks very similar to the Field Star Ragavan et al. 2010 distribution, where it's actually quite flat for most of the mass ratios. There's a peak near mass ratios of unity, and this fall off is mostly due to our sensitivity. So it's interesting that the mass ratio distribution sort of looks like the Field Star distribution, but the period distribution does not. So the purple lines here, this is the period or projected separation distribution that we would have expected from the Ragavan distribution from the Field Stars. But what we've actually detected is that the period distribution, or the projected separation, is actually further out, that it peaks at a larger separation than what is expected by the Ragavan distribution. Now, this has been discussed over the last decade by a variety of authors. Early on, especially with Kepler data, but those Kepler stars were much further away. It was also done with K2, but again, those stars were further away. And then recently, Carl Ziegler wrote a paper which showed this, but it was using SOAR data, where the resolution is about half as good as what it is on Gemini. So there were hints of this, but this was the first time we were really starting to see the statistics bear out. And so whatever's going on, the stellar companions are further out than they are in the general general field. And I would like to point out that the fraction of stars that are having stellar companions is actually remaining about the same. It's still about 45%. So it's not that there are fewer stellar companions, it's that the stellar companions are further out. And then finally, I'd like to highlight that the stellar companions appear to be hiding the smallest planets. So here's a quick plot, before I ran out of time, of the planetary radii and their periods. 4 stars that are single, so the lighter color are single stars, and the darker color are stars that we have found to be binaries. And you can see a very clear dearth of small radius planets in the single systems in comparison, in the binary systems in comparison to the single systems. And you can see that in this cumulative histogram, where the planet radius of binary systems is skewed to larger planet radii. So it's possible that this is an actual real astrophysical effect, but what it's more likely is that the stellar companions are hiding the smallest planets. And so when we start to do our demographics, it's not sufficient to think of all the stars as single stars, but rather you have to understand the multiplicity of those systems and the statistical likelihood that you would or would not have detected a lower radius planet based on the presence or not presence of a stellar companion. And so with that, I just want to put up my summary slide. And I do want to point out there's some posters of interest. In particular, I'd like to highlight Catherine Clark's poster, where she has a speckle survey of a bunch of M dwarfs, and where she's finding a dearth of stellar companions in these M stars that host transiting planets. Thank you.
Thank you, David. I see people typing in the Slack. So in the meantime, I'll ask a question. Can you go back to the slide where you showed the Ragavan period distribution or semi-major axis distribution compared to what you showed? So I think what you're saying there, by saying that the cumulative fraction is the same, like 45%, you're saying you don't think it's a completeness correction where you're just missing those planets between, 3 and 30 AU, that you think you're seeing them all because the number is the same. Can you elaborate on that?
Jesse, you said planets, but do you mean stars?
Stars, sure.
Yeah. So right. So the whole point of this was that we're doing that correction. We're making an estimate of what we're missing, and so these are corrected for what we think we would have missed.
Okay.
So the stellar companions that are simply missing at the smaller separations, and at some level that makes sense, right? You can't have a star and a planet be in the same, gravitational influence area and not disrupt each other.
Sure.
And this was.
So would you expect the purple if you just went out and looked at a random sample of 500 tick stars, you would have expected the purple distribution?
Yes, and in fact, we're actually doing that. We have a control sample program to do that. And of course, it's more complicated than that because, in the Ragavan sample, it's not necessarily the case that those stars are planet-free, right? So we do have a control sample which won't be planet-free, but it at least would be not transiting objects.
Sure, and presumably the Ragavan model included, there are probably planets in there, so I think that's fine.
And actually there was a great paper by Leah Hirsch, which came out this year based on radial velocities and imaging of a nearby sample. Granted, she was only sensitive to giant planets, but she clearly showed in her paper that the systems that had stellar companions and the systems that didn't have stellar companions had different planet rates.
Okay. I'm going to sneak in one quick question. Eric Jensen asks, when you say that the binary stars are hiding the small planets, just to clarify, do you mean diluting? Like, so they're just not being found in the Y curves?
Yeah, Eric, sorry. That's probably a much cleaner way of saying it. I should have said that what we think is happening here, unless there's some weird astrophysical thing that would make the small planets not show up, I think what we think is going on here is that the stellar companions are diluting the transits, and therefore you don't pick them up in the transit survey.
All right, and there's more questions for you in the Slack, David, but I'm going to cut us off because we're over the hour.
Yeah, sorry about that.
No worries. Thank you to all the speakers in the session and the great panel that we had. That's the end of today. See you tomorrow morning, same bat time, same bat channel, back here in room 1 for a panel on data analysis. Have a good afternoon, good evening, good morning, wherever you are. Thanks so much.
Thank you, Jesse. Thank you, everybody.
Thanks, Jesse.
Bye, everyone.